Okay, welcome everybody. Today is query optimization part 2. Last time we started with query optimization, and that was basically what we looked at is, okay, now we have a SQL statement. How do we get from a SQL statement to a program? How does the database system, or the SQL engine as we are calling it for the moment, execute or come up with an idea how to, given a SQL statement, what to do with that, how to translate that to a program, to a plan that can actually be executed. Because we cannot run the SQL statement as is. We have to do something. We have to do a couple of transformations. And one analogy I showed you was this picture, basically telling you, okay, depending on the type of system you pick, you will get very different performance. And the performance comes often from the type of query optimization you're doing. Yeah? So you have simpler systems like SQLite, which doesn't say that SQLite is bad. It's just saying for certain use cases, maybe SQLite is the right choice. Yeah? And for other use cases, maybe you need more performance. You need MySQL, you need PostgreSQL, or you need the modern DBMS, which are insanely fast. And there are use cases for flying through wormholes, but not that many. And we looked at some core ideas of that, and basically I showed you this cascade of translations we're doing. So basically from SQL we do what's called a canonical translation, which basically translates SQL into a relational algebra expression. And then we transform that through heuristic optimization, also known as rule-based optimization. So basically we apply a set of rules iteratively, having with the goal to improve the plan. No? And I also told you that be careful here when we talk about relational algebra. There are two ways of looking at relational algebra. One is to say, okay, that's something declarative and the order of operators doesn't matter. Or it's the more procedural way of reading a relational algebra plan that is, oh, the order actually matters. And in this discussion last week and today, the order of the operators matters. It makes a difference whether you first perform a selection and then the cross product, or first the cross product and then the selection. So the order matters, and that is used here in these heuristic optimizations. And then there may be another step we haven't looked at yet, but we will be looking at today. That's called cost-based optimization. And then after cost-based optimization, there's code generation sometimes. So like a compiler, like a C++ compiler, Clang, or whatever, you name it, we generate code. An executable code, similar to a compiler, is doing it for a general purpose programming language such as C++. However, we are in a domain-specific world, this data retrieval, data updating SQL world, very domain-specific. We can play a couple of different tricks that are not available to general purpose optimizers. And at the end of the day, we produce executable code, and then this code is executed and hopefully produces the result we declared for SQL in the first place. Yeah? So SQL is not executed, but some executable is executed, and that hopefully returns exactly the stuff we declaratively specified with our SQL command. That's the idea. Yeah? But we do not run SQL directly, of course. Yeah, and with that, let's jump into the second part of the slides. So we look at this stuff here, basically this from step 3 to step 4. So the transformed logical plan, so transformed meaning we applied a couple of rules, yeah, like this predicate pushdown rule, for instance, to execute selection predicates early on. We might have introduced projections, we might have replaced cross products by joins, and so forth and so forth. But now we run cost-based optimization. Yeah? And we will look at how that works. The general idea is, as alluded to last time already, so basically we are now in the world where it's not totally clear which plan is the best. So we have different options for plans. Maybe the supermarket analogy I mentioned last time already. You have 3D supermarkets. Which one do you go to? Which do you go to go shopping? So it's not such a clear decision, and you have to come up with a cost estimate. How much does it cost me to go to the supermarket? That doesn't mean just products you buy in that supermarket. It could be also time-wise. How long does it take to get there? How much does a ticket cost to take the bus or buy the fuel for your car? or whatever, or what's the quality of the products, or what is the stress level you're exposed to going to a certain supermarket where there are 1,000 other people doing their shopping. All these kind of things are phrased in the database world as costs. So costs may mean many different things, maybe in the total execution time, memory consumption, maybe whatever, network cost, whatever you want. That's a decision of the database architect to say, okay, that is a cost metric, the cost function I'm interested in. You might be interested in minimizing total execution time. You might be interested in minimizing energy consumption. You might be interested in minimizing memory consumption or network traffic, whatever. So all these things can be freely chosen, and the algorithms I'm about to show don't care about that. It's basically a parameter you can specify in those optimization algorithms to say, okay, that is what I want to optimize on. But so the optimization algorithms will be the same, it's just a different optimization goal you will be using. Yeah, so that is an overview. So basically, the high-level picture is something like that. So basically, we were in this world. Last week, we iteratively applied rules, and we never asked whether to apply a rule or not. We never looked at the costs. We always applied the rule, and that's called heuristic optimization. So the idea is, I have a rule, and if that rule matches, there's this match and transform part, as you remember, hopefully. So if there's a match on the input plan, you feel like, oh yeah, there's a match, then you execute it anyway, no matter what. You don't look at the costs of the transformed plan. There's no evaluation of a cost model in any way. It's just saying, okay, if it matches, I will apply that rule. And that works in 99% of the cases. It can go wrong in very special cases, but it's a good trade-off in the optimization space, so to say. Now we enter a slightly different world on the right here, where we say, no, we don't do it like that. We do cost-based optimization. That is, for any time we can make a decision, there might be alternatives. So here's like 4 alternatives for this plan 42. There's 42A, B, C, and D. And we are now in a world where we can't make the decision without looking at the estimated costs of these alternatives. So before taking a decision, we must estimate the costs. So basically, we create this plan and then run the plan through a cost function. If your cost function is runtime, so the cost function should give an estimate, okay, what will the runtime be for this plan without executing it? Of course, I can execute all of these 4 plans, but then, what's the point? So you want to know what is the plan costs, what the plan costs are, without executing the plan, and that's a difficult part. And then hopefully from those 4 plans you choose the one with the lowest cost under your cost model. Maybe that's 42D. And then there might be other options again, another 4 options for this plan, 42DA, B, whatever. Eventually you come up with a final plan that you want to execute, and that you believe will be the best plan or the one with the lowest costs under your cost model. And of course, all things can go wrong here. In particular, if the cost model is not a good predictor of the actual costs. That's a long story you will get to. But for the moment, is now we're in the world where we have options and we have to cost those. We have to come up with estimated costs for those options. And what are the different dimensions in here? So there are a couple of them. So one options that are created for different plans can be done already for logical plans, and the other can be done for physical plans. So on the logical level versus the physical level. On the logical level, already changing the join order. So if you have a situation like that, and you might also execute that. So here you execute first the join on S and T, and then you join the result with R. But you can also execute this by first joining R and S and the result with T. So if you're in a situation like that, where that is possible and join predicates are defined like that, well, you have an option. And that might have an impact on the cost model, as we will see in a moment. And notice that here I don't talk about a specific algorithm. Yeah, I'm just saying, no, there's a join operator. I don't care which algorithm is used to implement the join. This is a purely logical operator, and already there it makes a difference. That is why this is on the logical level. On the physical level, very similar things. There you can make decisions on, okay, which algorithm do I use? Which physical operator do I use for this logical operator? So when we introduced physical versus logical operators, I told you, yeah, for every join operator, for every logical join operator, there are a couple of algorithms, like these algorithms, for instance. There are many more. So which one do you use in your plan to execute this query? That's a decision the optimizer has to make. Another dimension is indexes. So we looked at B trees last time. So the two most important indexes, again, that's a repetition from last time, are hash tables and B trees. Hash tables are good for point queries. So there's just one value you're looking up. B trees can also execute point queries, but can also execute range queries. Everything greater 42, smaller 70. Yeah, that's hard to do with a hash table. There you better have some B tree to execute that. So which index are you going to use in your plan? Do you use an index or you don't use an index? Which sounds really trivial from a trivial decision from the point of view of the complexity, yeah? Because the index, has a better complexity if you have the option to scan your input and filter, that's like, and you have n tuples in your input, the complexity is linear in n, O n. And if you have an index, well, it depends if it's a hash index, it's kind of constant. If it's a sorted index by B tree, binary search tree, or a simple binary search on an array, that's kind of logarithmic costs and so forth. So it's kind of a trivial decision, you would say, that I will always use an index. If the index is there, I will use it. Of course, that's wrong, because there are situations actually in the storage hierarchy in a system where you can choose an index and you're 10 times slower or even worse than scanning in the first place. That may happen. Yeah, it sounds counterintuitive to complexities, but if the problem is that the complexities typically don't reflect the constants that the storage hierarchy has for doing certain types of access patterns. That's something for the core lecture where we look at in more detail. So the message for the moment is, sounds easy, in fact, it's not. Yeah, and then there are other decisions more on the physical level, of course. Which resources do you use for which subplan? So you could make decisions on how many threads do you use, which part of the plan get how much computing time, how much main memory is available, how you distribute the memory over the different parts of the plan, blah, 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 blah. Many, many, many decisions. Yeah? It's typically very difficult to consider all of those decisions. So you have to be greedy at some point. Yeah, let's look at the index space a little bit. So again, basically there's only two plans to translate a selection into something physical. So if you have something like this, a selection with a predicate on relation R, yeah, of course, you can do what we call a scan or a brute force evaluation of that plan. That means we examine each tuple in R and check if the predicate holds, if it's true. And if that is the case, we add the tuple to the result set. So we send it to the next operator. Yeah? And that's why I say it's O n complexity, because the number of tuples in the input determines the complexity of this operation, basically. Versus you do an index. Yeah? So we organize the content of R such that to evaluate the query, we do not have to examine each individual tuple to determine whether a tuple belongs to the result of a query. That's what I explained last time with horizontal partitioning. Yeah? You try to organize, you try to partition relation R in a way such at query time. So when you evaluate this predicate, you don't have to look at all of R, but just small subsets, ideally just the result set. And that is what the index is giving you. Yeah? So it routes you to an appropriate horizontal partition, a subset of the data that contains your result. Yeah? And it allows you to exclude large portions of the input relation are. Just routing you to a smaller subset, which of course then is much easier and much cheaper to evaluate. That's the idea of any index in the world. Yeah, and maybe to illustrate a little bit what's going on here, there's a nice visualization that's called Picasso diagrams. That was a long time ago, meant by a colleague from India. And it's pretty cool stuff. And I'd like to show a notebook on that because it gives you an idea on what the problem is and how complex the problem actually is. I need a couple of libraries here. So basically, to do that, I mean, you can do that with real query execution times. Yeah, so measure a couple of queries, measure different plans, plan alternatives, plan options, as we called it. But here I'm doing it with cost models. So basically, for the query, I have a cost model. So I have some predictor on how the costs will be. And basically, the constants of those cost models are defined here. This basically says that the sequential read of a specific tuple will be counted as 1. Note there's no unit here. There's not milliseconds or whatever, joule or bytes or something like that. This is free of units typically. Basically, all I need is a function that has the same behavior as reality. So if one plan in reality, one plan B, is faster than plan A, I want to have a model, I want to have a cost model that has the same effect, that in the cost model, B is also faster than A. In reality, B will be faster than A. I don't have to know by how much and in which unit and whether it's seconds or minutes, just the relationship has to be the same. That's the ideal cost model. Huh? And that's the idea of such a model. I always say a sequential read of a tuple will be counted by 1. A random read, meaning so you have to specify a certain position on your storage medium. You say it's an offset, tra-la-la-la-la-la, yeah, and then you fetch the tuple, and then you go to another offset, fetch the tuple. Those are called random reads, whereas the sequential means sequential read means the tuples are one after another on the storage medium, and then you go like, yeah, and that's typically a huge difference on storage media, and therefore it is reflected here. Then I have comparison costs to evaluate the predicate, and then I have the table/relation size specified here. And then I can come up with different cost model operations. So for instance, scan and compare, sequentially reading number of tuples specified and performing one comparison on each tuple. And basically here I return the calculation based on the constants I defined above. Yeah? So I develop here different cost models here also for binary search, for instance. Yeah, there's some logarithm as expected. And that basically gives me cost estimates. Now the query we will be looking at, we'll execute that. Okay, the query we will be looking at is something like that. So 2 selections, and we will be looking at 2 things. One is the order. Do we first execute P or do we first execute Q? And then also, how is the individual selection operation translated into an algorithm, into some physical operation. Yeah, we have our logical plan for that again, as in the other notebook. And then we have different physical plans. So we have quite many of those plans. We don't have to go into all of that detail. Maybe I just show some of them. Of course, you can full scan the stuff, yeah? Fully scan R and always check both predicates, which already is really stupid. Yes, the variant of that is you do a full scan, check P first. Only if that is true, you also evaluate the second predicate. Yeah, that's common sense to do it like that. But then, hey, it depends a lot on the selectivity of the different predicates. Maybe you better evaluate the one first that is highly selective, because the number of evaluations of Q depends on the selectivity of P. So if P doesn't filter out too many tuples, you will still have many evaluations of Q, and vice versa. So you want to evaluate the predicate that removes or that returns false very often, or more often than the other predicate. Yes, you order your predicates in a conjunct typically by their selectivity. The one that's removing the highest number of tuples is evaluated first, and then the second, third, fourth, and so forth. And how can I know that? Which one is more selective? No idea. That's what we learned so far. Right. Yeah, and then you have binary search and scan. So basically, here's the idea is you use the index on P, do binary search, and then you scan along the sorted data. It's basically available through this, what we learned last time in the B tree. So the B tree is a tree, yeah, but the leaves are linked lists, so the overall thing is a directed acyclic graph. But that allows you to do a point lookup. Yeah, maybe if you have an interval lookup, a range query, you can look up the left, from your side it says, the left boundary of the interval, go down the tree and then scan along the leaves, as long as the predicate holds. And that's how a range query is evaluated, and that's what I'm simulating here. Or alternatively, a double binary search, that means both boundaries of the interval are converted into point queries, and then you know everything in between is part of the result. That's the other way of evaluating that. Yeah. So basically, now what we do is, if you do a standard visualization of that, you could do something like that. You see that very often in query optimization. Basically, now you change one of the parameters. So the selectivity of the P predicate, again meaning few tuples are returned, one meaning all tuples are returned. Yeah? So, and then you look at the costs of the different plans, the cost estimates. If I say costs, I typically mean cost estimates. Yeah? So it's a cost estimate, and in the millions. So 1 million is returned here. And you see for the full scan, it's constant. The selectivity of P doesn't matter in this plan. For the index, however, and for the different index plans, I think they are positioned on top of each other, there's a huge difference. So selectivity makes a huge difference. For highly selective plans, you have almost no cost. The cost estimate is very close to zero. And that's a simple way of visualizing these things. However, this is not yet a Picasso diagram. Because the problem here is, okay, what if you want to vary more parameters? And I'll show that here without further ado. So here's what's called a Picasso diagram, and then it's basically a pivot table. If you think about that, so the idea is you have two parameters, one on X and one on Y, and then the color at each intersection, at each cell, indicates what is the best plan in that space. Yeah, so here you can directly read, aha, if I have these two free parameters, okay, everything above this diagonal is a dark blue, index start on P, and for the light blue below, it's index start on Q. Yeah, so you can directly read that. You can also do that in 3 dimensions. And that's super helpful to understand, given your cost models, so which is the best plan for these parameters. Yeah, and then you can play with your cost models, basically. That's what I'm doing here. So what I'm changing here is the costs for a random read operation. So back in the old days, that is what old people say. I'm already old, I say these. So when I was a student, we didn't have SSDs, we had hard disks, yeah? Really slow rotating platters. Yeah? And the problem with random I/O on hard disks was on the order of 5 to 10 milliseconds. So if you specified an offset in a file, there was a disk arm that had to be moved to that position on the platter, and that took like 5 milliseconds. Completely insane. That's millions of CPU ticks that are wasted in that time. Insane. So back in those days, in the 90s and even at the beginning of 2000s, database research had a huge focus on optimizing for random I/O, making sure that you don't burn random I/O. And that's basically what I'm varying here. So basically, if this penalty is high, the random read is very expensive, like on a hard disk, yeah, then you have a high number. If it's not so expensive like on an SSD or on DRAM or other modern media, then it's a very low number. So the difference doesn't, it's not that important. But the point here is, you see when you vary this parameter, say having different storage medium in mind, then you see different plans. Yeah? So if the penalty is not so high, it's just 10, you get a plan like that, here the red. So for low, so for highly selective things, you have these blue plans are the best. What was red again? Index start and end is then here the best plan in this space. Now if you increase the random read penalty, you end up with something like that. Here there's no change here, you see a slight change here, yeah, where the purple plans get better. Yeah? And that basically is kind of profiling your query optimizer, trying to understand, okay, given my cost model, what would be the best plan chosen. And what the cost-based optimizer basically does is, given certain selectivities, it will choose the plan that is indicated in the plan diagram. So if you know the selectivity of P is whatever, 0.5, and of Q is 0.8, it will choose the dark blue plan. Yeah? Anyone sees a problem here? To make that happen? Or any other questions? So now you implement that, okay, you have some algorithm, we will look into the details, that look at plan alternatives. You know there's a selection, you can use a scan, you can use an index, you first filter on P, first on Q, first whatever. So many options, you implement that somehow, whatever. But there's some magic ingredient missing here. Yeah? Yeah, how can I know the selectivities, right? All of this hinges on knowing the selectivities. If I don't know the selectivities, I can't make that choice. And that is why modern database systems collect all kinds of statistics. They collect statistics on selectivities. If you don't, your cost-based optimizer is not going to work. So a common pitfall, so these statistics are collected along all kinds of columns and tables automatically. Just one pitfall, some of these database systems don't do that automatically. So you actually have to actively trigger statistics collection. So one performance, if you have performance problems in database system, one of the first things you should find out is whether your specific system has up-to-date statistics. Because if it doesn't, it will choose crappy plans, and the plans will be bad and it will be slow. That's one of the first things you check when you run into performance problems with database systems. With database system, hey, whether statistics collected, are the statistics up to date? Yeah, that's a common pitfall in that world. Okay, so those are Picasso diagrams, and they can be more complex, but I think it's a very intuitive and cool technique to understand what's going on. So now let's look at join order a little bit. How difficult that is. It sounds so easy, but if you look at that from a theoretical point of view, where there's a tree structure, we have binary trees, and the number of binary trees for n input relations is actually given by the number Catalan n-1. That's the Catalan numbers. They appear all over the place in computer science. I invite you to look at the wiki entry for that. It's pretty cool. There's also tons of visualizations. But basically, if you just want to know the structure of a plan, so the possible binary structures, that's given by this number. So for instance, for two input relations, that would be C1. I'm going to have the example here, maybe it's more intuitive. Huh? So for three input relations, it's C2, and then you have two plans already. If you have two input relations, it's N2, that's C2 minus 1 is C1, and that's one plan. So there's just a single plan. But starting with three relations, you already have two options. It's this plan and this plan. Yes? This is also called a lefty plan, because you start joining two relations, and then you keep adding the next relation, like in a chain. Yeah? And here's a right deep plan. You start with two relations and keep adding relations, joining relations to the left. And that's why this is called a right deep plan. And those are structurally, so it's important to ignore here those input relations for the moment. Yeah? Structurally, those are the only two possible binary plans for three input relations. For four input relations, it's something like that. You have 5 plans. So this is again a left deep plan. Again, you start with 2, add another one, right deep, the same thing, add another one to the left. That's the right deep plan. And then there are these plans that are more like in the middle. Yeah, they're not so clearly left deep, not so clearly right deep. That's something like that. Those are called bushy plans. Yeah, all of these are called bushy plans. 5 options already. Okay. But then now okay, those are the binary plan structures that are available. I still didn't write down the actual relations here. Yeah. So the question is, how many options do I have to write down the relation names here for these plans? And that's a factorial number. Yeah? If you have n input relations, there are n factorial many ways to arrange them and then assign them to the different tree structures of a plan. Yeah, that's what factorial is about. Yeah, you have n input numbers, how many different orders exist on that, that's n factorial. So basically now you have to multiply those two numbers. So what is the number of structurally possible plans with the different annotations of the relations? Well, that's this number. So it's Catalan n minus 1 times n factorial many plans. Yeah, you guessed right, that's a huge number, and that goes through the floor pretty quickly. So here's a full example for 3 input relations. And here use variables a1, a2, a3 as inputs. I have those 2 structurally different plans. And now I have to combine that with the 6 different orders. So 3 factorial is 6, 3 times 2 times 1 is 6. So I have 3 possible assignment orders, assignment possibilities, so to say. I can assign R to A1 and S to A2 and T to A3 and so forth. So I would write R, S, and T, and that would be one plan. And the next would be R, T, S, and so forth and so forth. So only for this structure, this binary structure, I already have 6 different plans because I have 6 different ways to label the leaves of that plan. Yeah? And I have another 6 options here for the right deep plan. So in total, I have 12 different plans theoretically I could evaluate. Yeah? Is that clear? That's a theoretical, that's basically the space of possible plans that you can look at. Yeah? And then for each of those plans, for each of these plan alternatives, yeah, you can run that through a cost model. Yeah, and then you pick the one that has the lowest cost. That would be the naive idea of doing that. Yeah, so then you can do a reality check. So does it even make sense to list all possible join orders? If no join condition is defined between 2 relations, these relations must be connected by a cross product. Yeah, so it's basically also when you have a select star from R, S. And then there's no where clause and no predicate that specifies a joint predicate between R and S. So if you do select star from R and S is a cross product. Yeah, that is translated to a cross product. But then the question is, should I consider cross products and join orders? Yeah, so if no join condition is defined between 2 relations, these relations must be connected by a cross product. And that will be most likely be too expensive because the result of a cross product has a squarish size. Yeah? So it explodes pretty quickly. Why should we even consider this possibility in the enumeration? What do you think without looking ahead in the slides? Does it make sense to consider cross products or doesn't it make sense? Would I say, I mean, another way of putting that is basically, so here I'm always assuming that a meaningful join is defined. I'm assuming that there is some join predicate defined between A2 and A3. But maybe sometimes in the query it's not defined. If it's not defined, it's implicitly a cross product. Yeah? So basically what we are thinking about now is, okay, theoretically I have that space, I have 6 options here, I have for the left deep, I have another 6 options here with all these orders here again, the entire table, so 12 options. Okay, now I'm trying to make the argument, yeah, that's all nice theory, but if any of those options leads to, well, it's a cross product, why consider it anyway? The cross product is so expensive, it will most likely ruin the costs of the overall plan, so why not discard it in the first place? That is the idea here. Yeah? Rather than blindly enumerating the entire factorial times catalan, the insanely large space, I'm saying, yeah, no, let's ignore the cross products. Any intuition? Any idea? Yeah, it's also very hard to see, but actually, I mean, how do I start? Yeah, let's look at a couple of plans. See a couple of plans, and basically here I'm counting the number of intermediate results. And so let's look at this plan first. So this has 2 joins, this has 2 joins, this is 1 cross product and a join. And then I throw one of my cost models at that. One could be, okay, the number of intermediate results produced. Yeah? And that is basically this number plus that number. That's this 1,100,000. Here it's the same, 1,100,000. And here it's, oops, 100. It's only 200. Oopsie, that's so much cheaper than under this cost model. Yeah? And so you see, if you made the decision to just enumerate possible alternatives that have joins, and if you made the decision, no, that's a cross product, I mean, how can that be any good? But hey, it's 200 versus 1 million, it's a huge difference. Yeah? And actually, these plans are executed in certain situations by certain optimizers because they're so much faster. Yeah? And that leads to an entire discussion of, okay, why the heck did that even happen? I mean, my cost model should be a good predictor of a good plan, right? I mean, is that the right thing here? Is my cost model broken, or what's going on here? Should I really execute this in a real system? Actually, you don't. You do other tricks. Yeah. So actually, this alludes to problems with the cost model. The bigger story behind that is, when you remember, I said these joins always have 2 inputs. Yeah, and that's a join operation in relational algebra always has 2 input relations. It could also be an alias to the same relation if you have a self-join on the same relation. But anyway, it's 2 input relations. And that's the constraint in relational algebra, and that's complete crap. It's complete crap because it excludes a plan where you join an input relation with multiple other relations at the same time. So in reality, how such a plan is translated is an a ternary join. So there's one input relation, and it is joined at the same time with multiple relations. So discarding that constraint from relational algebra. Yeah? And the problem here is that this cannot really be expressed in binary trees. And therefore, you end up with a very artificial cross-product kind of thingy you would never do in the algorithm, but still that alludes to, yeah, maybe that's kind of the thing we should do. Yeah? But it's a problem of this constraint. So again, this is another hint to whenever there's a constraint in computer science, question that constraint. Make sure you understand why the heck is there that constraint in the first place. What did those people think about when inventing that constraint? Yeah? And this constraint that a join should only have 2 inputs cannot be justified. That's legacy, but cannot be justified. And that's an example for that. So bottom line, yeah, if you want to find the optimal plan under a given cost model, in the general case, I'm sorry, but you have to enumerate cross-product plans as well. Yeah? The confusion is when you look at certain algorithms, and if you look at literature or if you read about that in books, often these algorithms ignore cross-products because for the 95% case, that's okay. Yeah? Many algorithms, many papers make that restriction and say, yeah, we ignore cross-products because, in the general case, it doesn't help. Yeah, but there are cases where it makes a huge difference, and not just by an epsilon, a huge difference. Yeah? So just be careful when you look at techniques, what people are talking about. Good, so cross-products. Now let's look at joint selectivities. So that's an important term you run into when trying to make decisions on an optimal join order. So by joint selectivity, we already had selectivity, if you remember, when you looked at these predicates that can be expressed on a single input relation. Now we look at the selectivity of the join. So how many join tuples are produced by the join compared to the number of total of possible join results. If you look how many join results are possible, well, that's the same as the number of tuples in the cross product. If you have a join predicate that is defined as return true, no matter what, then you have then the result is equal to the cross product. So that's the maximum number of results. And then I basically count, so that's a cardinality again, number of tuples here in questions? Number of tuples here in the cross product. And then here the number of tuples in the join, and that gives me a number that's smaller or equal 1, obviously. And that gives the join selectivity. And here's an example of that. So I have three input relations with 1 million tuples each. I have different join selectivities here expressed, and with that I can do the cost estimate. If I know that this join will produce 1,000 input tuples, then I can use those 1,000 tuples to compute the result to that cost intermediate results cost model. If I know that, if I know the selectivity. If I don't know that selectivity, I can't evaluate that. Here's a little, another selectivity that's 100 times more tuples. So 2 orders of magnitude difference in those two selectivities. So that will lead to a higher cost, obviously. And with that kind of statistical information, you can evaluate the different join orders and then make an informed decision, hopefully. So we need a couple of things in terms in the following discussions. So one is predicates. We had that already along when talking about selections and joins, of course, but the more general form is something like that. So predicates are expressions defined in where or on. For example, we had an example here before. That's the predicate, of course. Joint predicate is somehow defined in the join, and the selectivity of the joint predicate is something like that. In general, a predicate is a formula in conjunctive normal form, and you had that in some other undergrad lecture, I guess. Basically, it's a composition of literals. So literals are these expressions comparing typically a variable with a constant. It could also be multiple variables. That must be 42 in this case, a product of those variables and so forth. Those are called literals. And those literals are connected into clauses. So that's basically a disjunction of two literals. And all these clauses are connected through an AND operation in a conjunction. So that's a big conjunction, and that's then in CNF. One other term is the arity of a predicate. That's very useful in the further. My voice is going down. That's the arity of a predicate. So that basically refers to the number of relations being referenced in a specific predicate. So whenever you define a predicate, you may let's look at the examples. You use a reference to an input relation somehow. Here it's relation R, and this predicate here has arity 1 because only one input relation is referenced. Here it's 2 input relations being referenced, here it's again 2, and here it's even 3 relations being referenced, and that defines the arity. So how many relations are referenced in the predicates. And that leads to an important distinction, because 2 special cases we will be focusing on. Of course, you can also look at other cases, but 95% of the time you will only have these kind of predicates. So one is filter predicate. So basically, you only reference 1 relation, and any filter predicate can be pushed down very far down towards the input relation. So that's typically what you push down in this predicate push down. The other is a joint predicate. That's referring 2 different attributes, and that's something typically you use to rewrite a cross product plus a selection to a join operation. Those are the 2 kinds of predicates that you should look out for in plans. Okay. Yeah, a very important construct that is used in cost-based optimization is a so-called join graph, also known as a query graph. It's basically a structure. Maybe let's go to the example directly. It's easier to grasp. So basically what you do is you represent each input relation as a node. Yeah, so here we have a query where there's 4 input relations, R, S, V, and T. You represent each joint predicate specified in the query through an edge. So that's a predicate of arity 2 again. Yeah, otherwise it doesn't make sense. All of these edges have arity 2. And of course, there are joint edges that might have arity 3, and then it becomes a hypergraph. Yeah, we don't look at that. But here it's a simple graph with 2. Did you have hypergraph? Do you understand the term? Did you have it in some lecture? That's an extension to, so in a standard graph, an edge always connects 2 nodes. In a hypergraph, you have edges that connect more than 2 nodes. Don't try to get that right in your brain visually, because an edge connecting 3 nodes is very hard to scribble. Yeah? So it's more like a space, yeah? Like an area, something like that. That would be an edge in the hypergraph. Yeah? But with that, you could represent predicates with arity strictly greater 2. Yeah? We don't do that here. We just have these edges that connect, so simple graphs that connect 2 of these nodes. Yeah? And you see it here, it always has arity 2. Yeah? Here I make the assumption that A is from one relation and E is from the other relation. Then you also have predicates of arity 1, as introduced before. Well, and they're annotated directly here with the relations. So basically, what you see here, you get the predicate pushed down for free already. Yeah, they are already pushed towards the nodes. Yeah, you don't have to do this artificial rewrite as we did in rule-based optimization. You already get it for free here in this kind of visualization. Yeah, and with that you get different join graphs. Here's another query with 3 input relations. Here's a one with 4 input relations and 4 edges, and so forth and so forth. And basically, then you define a query graph like that, where you say, yeah, you have a set of relations. Each of these relations is a vertex, aka node. Then you have the joint predicates that form the edges. Those are the predicates of arity 2, as defined before. And then there are these filter predicates, which are annotated, with the vertices as defined before. Those have arity 1. That's all you need for a join graph. There are extensions for that to extend it for grouping, having and stuff like that, but that goes beyond this lecture. Yeah? So for the moment, we have join graphs, aka query graphs, that represent the joins, that represent all the filter conditions, so the of arity 1, yeah, filter conditions, and the join conditions. Yeah? That's all this what this represents. And so you have a node. Okay, so sometimes we use dot notation, sometimes not. So both are fine. You could also write something like that. That's okay. Also for the exercises. If in doubt, rather use the dot notation. So for instance, here it might not be totally clear where that attribute C comes from. Is it an attribute of S? Is it an attribute of T? Well, T already has a C here, so maybe it's from T, and maybe A is from S. Yeah. But if in doubt, write it explicitly in a dot notation, and there's no confusion happening at this point in time. Yeah, with that, let's look a little bit at our second notebook for today about plan enumeration. So here we have a concrete scenario. So that's basically a drawing graph. So you have here these 4 input relations A, B, C, and D. We also annotated with the cardinalities. Yeah, so that's basically what this is trying to express here. 4,000 tuples are returned, 1,000, and so forth. And then we have the edges in between those nodes, and we also draw the edges in a different width. Yeah, so the thick, the really fat edges indicate edges that are highly selective. So for this edge, for instance, you have 0.003 selectivity, whereas for this 0.37, so every third tuple will be produced by the join result. So that's a thin edge. Yeah, so this also visually means if there's no edge, if this is equal to the edge being super thin, so thin that you don't see it, this is equivalent to, yeah, it's a cross product, because selectivity is so low, you don't see the edge. Yeah, that's the idea. Yeah, so that's converting this binary world from, or extending this binary world from there's no edge, so it's a cross product. There is an edge, so it's a join. This is somewhat a continuous space I'm showing here. So that's saying, okay, the bigger or the thicker the edge, the higher the selectivity, the more it feels like a real join that's actually only selecting a couple of tuples rather than a large subset. Yeah, and then you have methods to compute costs and defining plans. I have to go through it. We don't have too much time, but basically the same we looked on, we saw on the slides. And I have a left deep plan on the 4 input relations with one random annotation of the leaves. So that's a random order. C, B, D, A could be any other of the orders, but that's the random order I picked here in the notebook. And now I define a cost model that's basically looking at the sizes of the inputs, similar to what we had in the slides. And with that, you can basically now compute the costs. Now, once you have a cost model, you can throw the cost model at the specific plan, and then you get a number. Again, the number has no unit. That's the same thing you will be seeing in a real system. So real SQL engines allow you to look at this plan. You can expect the plan. You submit a SQL query to a database system. The system will translate that to a plan. The system will come up with a cost, and you will see the cost doesn't have a unit. Yeah, if you want to play with that already, so typically all you have to do is, rather than sending a SQL statement, you prefix it with explain. Explain, select star from tralalala, or explain, analyze, depends on the product. And if you do that, you get an explanation where there's something like that. Yeah, sometimes it's not a graphical, for Postgres, it's a graphical representation. Other explanations are textual, but basically you see the plan the database system uses for this SQL statement. You can inspect that and take a look. It doesn't make sense. Oh, it doesn't make sense. Maybe the statistics are broken, or maybe there's an index missing, and so forth. So that's basically a profiling tool, if you want, to estimate this stuff. So there's a number being computed by the cost model here. Yeah, and then of course you can brute force over the random orders here, basically enumerating along the factorial. Here I do that for 4 only, 4 random plans, and you see, okay, the costs vary a lot. Here you have 1.2 million, here it's less than 1 million, 2 million, 127,000. So that looks good. That's relatively cheap compared to the other plans. Yeah. And then you can, of course, exhaustively enumerate that. I think it's done here. And I do that here. And I only draw then the plan with the lowest cost, and that's this one that has 61,000. And yeah, that's basically what the optimizer is doing. So there's one algorithm. I'm not saying it's better than blindly enumerating all of the possibilities. There are better algorithms than that. But at the gist, the core idea is that you enumerate the different plan alternatives. Each plan alternative is passed into a cost model, and then you check whether that's better than the plan you had so far. At the end of the day, from all the plans you enumerated, you pick the one with the lowest estimated costs. And that will be used to generate code, and that will be executed by the system. That's the idea at this point. Huh? Yeah, and for our IMDb example, we also have here in the notebook the query graph, aka join graph here, also with the selectivities. Yeah, and then similar to what we have seen before. And then basically you can enumerate the cheapest plan here. And this is only, you see the runtime here. I think it's around 20 seconds or something like that. You have to wait a little bit. So basically, I'm enumerating all the different factorial orders just for the left deep plan. Okay, it's Python, but hey, this is a complexity thing. C++ won't help too much. So 16.7 seconds. It's actually 3 times faster than on my old machine. Pretty cool. Okay, so basically that's the left deep plan. Yeah. So if I fix the structure of the binary plan to be left deep, all I did here was doing all the possibilities to label the leaves. That's all I did in 17 seconds. Yeah, I didn't look at different binary structures yet. That would be much more expensive with such a naive algorithm. Yeah? You see already how quickly the costs explode for something like that. So you have to be careful. That's one pitfall in optimization algorithms. Yeah, of course, you can run a sophisticated optimization algorithm, but if the optimization algorithm uses more time than a stupid plan in the first place, so what did you win? Nothing. You lost. Yeah, you always have to look at the overall time, optimization time, and then the query execution time. And you want to optimize the sum of that. Yeah, if you do little optimization and execute a stupid plan, whereas you do optimization like that and then you execute that plan where the sum of the latter is bigger than the stupid plan stuff. So, yeah, so there you have to be a bit careful in these algorithms. Yeah, any questions about that? No, okay. That's basically just giving you an idea on take a look at the notebook. I invite you to do that. Typically we have an exercise on that where you should extend the notebook. I'm not sure this week. But you should take a look at that. Huh? Okay, so now we look at certain aspects of enumerating those joins. So one is commutativity. So when you look at these 4 plans, for instance, they all have the same costs under this cost model where I count the intermediate results. They all have 1,000 in the middle. You see that here. Yeah, and then the 100, of course, is here. This also, typically, you can modify this thing, the cost model, to ignore the 100, because no matter what plan you will come up with, the query result will be 100. So what does it add in terms of information? Nothing. Yeah, the query result must be 100. If you come up with a plan where the number of tuples is not 100, well, maybe the plan is wrong here. Yeah, because for all plan alternatives, the query result must be exactly the same. So this must always be the same number for different plan alternatives. So why use it in the cost model anyway? It doesn't carry any information. Yeah, so that's a typical modification you could use here. Anyway, so this number is the same, yeah, for all of these plans. So which one do I execute here? And so when you think about that, you quickly get into a discussion where, okay, yeah, this logical join order is interesting, but you also have to look at the physical algorithms. And one, or the most important join algorithm is called the hash join algorithm. And it's relatively easy. So what you do is, so a precondition is that you have an equality predicate. So something like along a foreign key constraint, r.x equals s.y. Yeah, so that's your joint predicate. And what you do is, conceptually is, you build a hash map on one of the inputs. That's happening here. That's also called the build phase. So everything from R, you take each tuple from R and insert it into the hash map using r.x as a key. You note that is the one, that is exactly the same attribute that's referenced to in the joint predicate. Yeah? So everything from R is inserted into the hash map. That's called the build phase. And then there's a probe phase, that's this here. Basically, now you look at S, and for each tuple from S, you do a lookup into that hash map using column Y. Yeah, that's basically what happens here. You probe or search or get or however the function is named in your hash map, and then you check whether that returns the result. If it returns the result for the key, so if that is not empty, it's not the empty set being returned, so there is an entry for that, then you append this to your result set of the join. Can anyone explain to me this expression? Result, union, bracket. Why doesn't this work? This expression. Why do I do this? Build the hash table on one input, on input R, with respect to the attribute used in the join predicate. So I built a hash table using r.x as a key, line 4. Yeah, loop over all inputs from R, line 3. Eventually, I inserted all elements into the hash table. That's the build phase over. No? I basically created a hash map on all of R. Now comes the second phase, starting line 5, that's the probe phase. So now each and every tuple from S is probed against the hash table built on R. Yeah, so I don't probe with R, I probe with S. Each tuple from S probed with S.Y against the hash table may or may not produce a result, may find a tuple in the hash map. Right? And then what the heck is line 8 about? Yeah? Mm-hmm.
And we are appending it with the cross product of the RAS and the S entry,
mm-hmm.
which is only a tuple, but it's marked as a cross product. But
Yeah.
a single entry and S.
No, you can assume that it's not duplicate free. So what I'm inserting, the hash map is able to collect entries that have the same key. So there might be two different tuples in the hash map that both have the key on x42, for instance. Now if you do a lookup with s.y with 42, the result set will return multiple tuples from R. That's my assumption here. I mean, it depends on actually the cardinalities of those columns. So sometimes often you join on the column where one is a key, and then there is no duplicates, yeah? But the other column, typically the foreign key column, has duplicates. And here I don't specify that, I just say whatever, I have no idea, yeah? So then I say, okay, I basically assume that the hash map may contain duplicates with respect to r.x, and then I do a cross product in line 8. Why? Yeah?
So we're basically then connecting each of the results which from the join out of R, and we're connecting them to the corresponding data that we took out of S.
Right, exactly. That's the explanation. So each result that comes out of the lookup is connected to the lookup tuple I used. So S was used as a lookup. And if you think along the lines of the predicate again, you want to identify, if you execute the join like I do the cross product and then I do the filter and I want to keep all of the tuples where the join predicate is true. That would be all of the tuples in the cross product that are connected with S and any tuple in the result being returned here. Yeah, it's not just one tuple being produced here, it may be multiple tuples. The number of tuples returned by the probe operation defines the number of tuples returned to the join result. And that is why this has to be a cross product. Very good. That's the answer. Yeah? And then in practice, you typically try to run the join in a way that you are aware. So if you know it's a key column, okay, you don't have duplicates, and you know the hash map doesn't have to support duplicates, blah, blah, blah. So many tricks you can play. But in the general case, you have to do something like that to not miss any entries. Yeah, make sure you look at this algorithm because it's really crucial in query optimization. And this variants of the algorithm are also used to implement intersection, they're used to implement difference, they're used to implement grouping and aggregation. It's always the same algorithm, 2 lines are different basically. Okay, but in terms of costings, that means, okay, now we have an algorithm that doesn't have symmetric costs, because you could make the argument, yeah, okay, on R I build the hash table, and then on S I use it for probing. And if you translate that into constants, so you have number of R tuples that are being inserted, each insert costs like C1. Typically, a probe in the hash table is slightly cheaper. Yeah? So you have number of tuples from S, each tuple is probed against the hash table, and then you have a constant C2. And C2 is typically a bit smaller than C1. So it does matter whether, it makes a difference whether R is the probe input, the left input, or S is the input. Makes a difference in the costs in this model. Of course, if C1 equals C2, it doesn't, but that's not a good way of defining C1 and C2. Yeah? So how you set those values depend on many factors. Actually, this was really an eye-opening study we did a long time ago, because until then I was assuming, yeah, there's a hash table, it has constant insert and lookup time most of the time, except the pathologic cases. No. Actually, there are tons of different hash tables, hash functions, and tricks you can play. And they have a huge difference in performance. Yeah? So it's not so easy. It's not you pick a hash table and then you get the best performance. There are many, many tricks you can play with hash tables. And it's not just an epsilon in performance you gain or lose. It's a huge difference. Yeah? So it's again, something where you can do much more to gain performance. Yeah. So an asymmetric cost model we're seeing here. But then you can also look at memory. Yeah? If you think about that, hey, okay, so what kind of memory do I have to keep for such a join? Well, if you hash all of R, all of the build input into a hash map, yeah, then you better have the memory for that. So it is kind of natural to assume, okay, I take the smaller input relation. Yeah? Take the smaller input relation for the hash join and use that as a hash to build the hash map on. And then when you do a cost model to that, you see here, you could do something like that. So that's basically the costs for main memory. So here you could do something like that. That's the overhead of the hash map for storing an entry. So there's some data structure overhead you have. That's the size of the tuple. You multiply that with the number of tuples being stored. And so overhead is a factor of that, whatever 1.21 for 10% or something like that. And that's the overall cost. But there's no cost for S. Yeah? In this cost model, you don't factor in the costs for S. You say, okay, loading one tuple from S, I don't factor that in. This is all you need to do for the cost model. Yeah, so that makes a huge difference. This actually leads to, assuming on a situation where you store like 1 megabyte relation with 1 exabyte. Yeah, that's an easy choice. Yeah? Okay, so 1 megabyte maybe should be the build input. There you create the hash map, and the 1 exabyte at no point has to be loaded into main memory. It's only one tuple at a time has to be probed. Yeah, so the hash join can be used for so-called external memory joins, where one of the relations doesn't fit into your storage medium, like main memory. Yeah? One sits on some super extensive storage network, yeah, but you don't have to load the one relation into main memory. You just have to build the hash table on the small relation and then probe the other relation to that without loading it. Yeah? So if one of the relation fits, you can run the hash join. Yeah, and then when you look at that, now here we're extending our cost models. You see, with respect to main memory, we have a couple of differences in the plans. Before we didn't have differences with respect to intermediate sizes, but now you see, oh, now I have 2 hash maps with 1 million tuples here. This is much better. There's only one with 1 million tuples, and this only has 1,000, because here I'm only creating the hash map, of course, for the tuples that were created by this join. As this join is very selective, I only have to put those 1,000 tuples into the hash map of the top level join. So you see a difference in this cost model, which of course means, okay, you better pick one of those plans with respect to main memory. And then you can combine those models. That's what's happening here, where you see, okay, there's a lot of data coming here. This is not so much data coming here. And then basically you see that both of those plans are similar in costs, right? Right, left SRT, right, with respect to main memory and the intermediate results, both are the same. Yeah, and then basically you can combine those cost models. Yeah? So here you have a cost model that is consists of a main memory cost model, intermediate cost model, and then you have some weight factor on top of that, and then you can play with that, whether that helps you in optimization. And it's an endless story, yeah? how to create those cost models. Yeah, and then at that point, I think on some slide already I alluded to that. So computer scientists have a tendency to, once we have a model, to never look back at reality. Hey, we have a model. That's our playground. That's our fantasy world. That's our Minecraft. Yeah? This is my Minecraft fantasy world. I have the cost model, and I come up with an optimization model in that world. The same happened for this. Okay, I exclude cross products and plan enumeration. I just look at the query graphs. I just enumerate along the lines of join predicates. That's my fantasy world. That's my Minecraft world. And I ignore reality. Reality is cross product plans can be better. No? And here's the same thing, where I strongly recommend to frequently check back your model with reality. At the end of the day, you don't build the model to have fun and play with that and have a thinking exercise. At the end of the day, you're trying to solve a real-world problem. So it makes a lot of sense to synchronize reality with your model, to check back, oh, is the model really reflecting what I'm trying to express here? And when you look at these two situations, for instance, the question is, does that reflect reality? So what I'm trying to say here is, okay, if I do something like that, I have a very small hash table, 1,000 tuples, here it's 1 million. It's clear I do that because what I can do is I don't have to load all of T into my memory at the same time. I just read a batch of tuples at the same time, or just one tuple at a time that has to be kept in my memory, and then one by one, without allocating space for all of T at the same time. But when you look at our implementation, that's not how it works. In the Python notebook, you will see that we call in this evaluate method the evaluate function of the input operators. So if a hash join has 2 input operators, we call this evaluate method, and that materializes the entire input. So this is in conflict with the model I just explained. So the implementation is not doing what I just said. I said, oh, you can stream the right input. No, the implementation is not doing that. The implementation is materializing. It's copying the entire input into my memory, which is not the best thing you could do. So there's a mismatch. Okay, now we found that this implementation is not doing what our cost model is doing. So what can we do? Yeah, someone else? Huh?
I can adapt the cost model
Exactly. Those are the two options. Yeah? So we change reality or we change the model. So we changed the model. Yeah? So we could say our model from above was something like that. Yeah? Okay, just considering R. Okay, but in fact what happens is something like this. That is the original cost model. Plus, hey, no, actually we also store all of S. That would be one way of doing that. Or we change reality. Yeah? So everything is materialized for each call. This is actually unnecessary, and no real query engine would do something like that. This is just toy notebooks here for the lecture. And what you can in fact do, you can, for many operations in a plan, you don't have to materialize the entire inputs. Yeah? Very good examples are selection and projection. For a selection, to filter out, you can make a decision based on a single tuple. Yeah? You inspect the tuple, and then you can make a decision based on the predicate, yeah, qualifies or doesn't qualify. You don't have to look at all of the data, just one tuple is enough. Yeah? So it's independent from what comes afterwards. The same for projection. Yeah? You don't have to know all the data, one is enough. Of course, if you do duplicate elimination, it's a different story. Yeah? They have to be more careful. But if you ignore duplicate elimination, you can decide it on an individual tuple. For aggregation with a maximum, for instance, you don't have to look at all tuples at the same time. You could also keep just the maximum you've seen so far. Yeah? Look at one tuple, that's your current maximum. Look at the next, oh, that's even bigger, then I keep that one, discard the other, and so forth. So it's just a running maximum you keep in that operation. Yeah? And that allows you to save a lot of precious memory. Yeah, and that basically leads to another discussion in these plans, that's pipelines, and in particular pipeline breakers. Ooh, running out of memory here. Running out of memory, not running out of time. So basically, what you observe in these plans is that at certain points in the plan, the data must be materialized. So if you look at the hash join again, you see, okay, here this is kind of a this is called a pipeline breaker or materialization point because all of R is put into the hash table. Then when you look at S here, you can directly parse because basically what you do here is each tuple from S is probed against the hash table, but you don't materialize all of S into a main memory structure. That's not needed at this point. But then again, the results here are put into a hash map again, so that's again a pipeline breaker. So the pipelining process is stopped. Yeah? And then you can look at different plans where the pipeline breakers are, and also, yeah, think about whether that's a good way in the optimization or whether you want to have something like that. Yeah, and with that you can also identify plan sections, and that's very important to understand how code is generated for such pipelines. So basically a plan section is a fragment of the plan starting from any leaf up to the next pipeline breaker. You see it here. So this is one plan section, yeah, from R to the first pipeline breaker. This pipeline breaker is the insert operation, the build operation on the hash map. Then the next plan section is this, from S, probing this hash map, building the next hash map here. And there's a third plan section, that is this one, from T, probing the hash map here, and then producing the result set. Those are plan sections. And in the interest of time, I have to shortcut here a little bit. Yeah, and once you identify those plan sections, you can do code generation. So now we're in the final step, basically, of the query optimization pipeline. Not the final, okay, the final is execution, of course. But now let's look for 5 to 10 minutes a little bit at this here. Now, once you come up with a physical plan, so your cost-based optimizer identified the most promising plan. Everything is physical. All operations are physical. And the optimizer told you, yeah, that has the lowest cost under the cost model I was asked to optimize it on. Now you still have more options. And one is to do what we call plan interpretation. And the other is code generation. So plan interpretation is what you see in the notebook. We don't do a real code generation. We have pre-canned algorithms that are just assembled. So basically the physical operators used in the notebook are just connected to each other in the notebook when you define those calls. They're connected to each other, data is sent around, but that's not code generation. What a real system should be doing is real code generation in the sense that now you have the physical plan and now you output somehow code that can be executed. That code can be LLVM, this could be WebAssembly. You could even generate C++ code and feed that through a compiler which generates a binary and executes a binary. Why would I rather use LLVM or WebAssembly rather than producing C++ code? Yeah, what I just said is basically now you have your plan. Yeah, that is your physical plan, and then you have here two hash joins. And maybe you also said, okay, that's an index access, whatever. You could translate that into a C++ program. Run it through a compiler and then have an executable, and the executable then produces the result to the query. Yeah?
Maybe not that efficient because the C++ compiler isn't that fast and also looks for a lot of optimizations that are not necessary.
Yes. Exactly, that's the answer. So compiling in C++ is not, the C++, okay, you can switch on and off different optimizations, but again, C++ is general purpose, and the focus is not necessarily there on optimizing compilation time. That's not the goal of a C++ optimizer. Here, however, we are in a world that the query comes in, and you want to optimize the end-to-end time. So once the user submits a SQL query, he or she expects the result to come back very quickly. So if you spend a lot of time, again in optimization we had the problem, optimization time shouldn't be that big, but also here the compilation time shouldn't be that big, because it's all part of the overall bill. Yeah? So the compilation time should be fast. So going via C++, going via a text file that's then parsed and compiled and whatnot and takes a lot of time, is typically not the best solution. So you need something faster. Yeah? And with WebAssembly and LLVM, you can use APIs and stuff, and it's typically way faster. And here's an example of code generated for that. So this is basically pseudocode, what you could do. So you have two hash maps. Now you add all tuples from R into hash map HM1. That's this one, this plan segment. This is this first plan segment. Yeah, that's looping over all tuples from R and inserting that into this HM1 hash map. That is the first segment, this gray segment, A1. Next segment, A2, yeah, it's this one. So for all tuples in S, you probe hash map 1. If that is a result, you produce something like this cross product thing we discussed before, and insert that into the second hash table here. Yeah, this gives you the second segment. Third segment, this one. Now for all tuples from T, yeah, this one here, you probe this hash map HM2, and then if that produces something, you yield, which means you deliver it to whoever consumes the output of the query. Yeah, that's basically how you create code, and then you can create that code using whatever API or underlying execution language. Yeah. And that then also translates to multi-threading. You can, okay, basically have one thread for horizontal partitions. For each horizontal partition, you have compare and swap hash maps that are protected against conflicts and inserts and stuff. So there are many extensions, so you can do that, but that's more something for the core lecture. Maybe just to wrap up, because if you go back to this big data term, I said that already at the beginning of the lecture. So if you have really large data sets, sometimes referred to as big data, so one of the most popular systems in that space is called Spark. And when you look at the explain analyze, yes, so the plans that are being generated, and here's an example on the slide, you see each and every element I explained in this lecture. Yes, there are logical plans, there are physical plans, there are plan segments, there's multi-threading exactly as explained in this lecture. So that's used as explained in this lecture. And that's super useful to profile those plans and understand if there's performance problems, what the heck is going on, can I improve those plans? Okay, to wrap up. So what do I do if the queries are too slow? How do we get from SQL to an executable program and principle through automatic, heuristic, and cost-based optimization? What are the tasks of cost-based optimization? That's what we focused on this week in contrast to last week. So the tasks are enumerating, plan alternatives. Yes, you require statistics and cost estimates for that, otherwise it's not going to work. You can make decisions on the join order. You can make decisions on the physical operators / the algorithms being used. You can worry about how to pipeline data, worry about blocking versus non-blocking operators. You can plan multi-threading and so forth and so forth. So there are many options you can consider during planning. Then there's code generation. So once you identify the physical plan, how the heck do I execute it? It's just a tree with physical operators. How do I execute it? The easiest way is to do interpretation. That's what's used in our Jupyter notebook. But in a real system, you do code generation, and you really output a program that calculates the result of the query, and you shouldn't waste too much time generating the code on the way. And for all of these topics, we just scratched the surface. There are many interesting techniques in this field, actually. Colin, and then I don't say anything. That's kind of a cliffhanger, right? No, okay, maybe the Colin's perspective. So there's some further material if you're interested that you don't have to look at that for this lecture, but that's actually part of the core lecture that will also happen in winter term. Yeah, there we go a bit more into detail. For this winter term, there will be way more material than the stuff in the videos. If you're interested, you can peek at that. There's also a book I wrote a couple of years back with some material. If you're interested, you can download it for free. Yeah, that's it for today. See you next week. Yeah? Thanks.